we are going to be able to calculate the position of where our equilibrium is. So we've got a cute little cartoon Erlenmeyer flask there with the solution of things, and they say, boy, I'm sure glad that they evaporated, and they come back to the party and they say, uh-oh, well, I'm getting out of here because it's too full now. So we have this constant going back and forth to make sure that we are staying at equilibrium, and when we change things, then the solutions have to change in a way to get back to that equilibrium. So let's take a look. Some of the things we know that we need to do if we want to change the rate of a reaction. We know we can change temperature, we can change pressure if we're dealing with gases, we can change the mass of a solid if we're dealing with solids, or surface area of that solid if we're dealing with solids. If we're dealing with aqueous solutions, and that's what we're going to be talking about predominantly today, we can deal with concentration. So the equilibrium constant, we have a symbol for it being K, capital K, and then a subscripted C. Oops. The science definition of the equilibrium constant is that the concentrations of the products, so we know the concentration is moles over liters, of the products raised to the power of their stoichiometric coefficients. That means the value that's in front of the numbers after we've balanced an equation, is going to be divided by the concentrations, again moles over liters, of the reactants raised to the power of their coefficients. So we're dealing all with molar ratios and concentrations. So we allow a reaction to reach equilibrium, and then we measure the concentrations of everything. We can then combine those values that we've calculated to determine mathematically the value of our equilibrium constant at a given temperature and pressure. The equilibrium constant always has the same value, provided that we're not changing the temperature, irrespective of the amounts of A, B, C, and D that we start with, assuming that we have an equation like we saw in the last notes with A plus B goes to C plus D. It is also not affected by a change in the pressure or whether or not we're using a catalyst. If concentration remains constant, we're not going to look at it. So if we're dealing with solids, that concentration is not going to change. So we are not going to look at the values for solids because the concentration is not changing. Or if we have liquid water, if we have this aqueous solution and one of the things is H2O. Anytime we have liquid or solid, we're not going to be dealing with them as we're calculating our equilibrium constant. So, it's going to provide a measure of the equilibrium's position. If the K value is larger than 1, the products of the reaction are favored. If K is small, the reactants are favored. So our grand equation here, Kc, the equilibrium constant, in terms of concentration, that's what that C stands for there, we've got the square brackets that we've seen many times before, which means the concentration, moles over liters or moles over decimeters cubed, moles to the decimeters to the -3, and then raised to the power of the coefficient. So we need to look at our balanced equation to figure out what our coefficients are. Okay, so we have here our first reaction, water plus carbon is in equilibrium with hydrogen and carbon dioxide. So number 1, must all substances be accounted for in the equilibrium constant? Well, I need to look at what types of values or what types of items I'm given. I have gases and solids. Well, no, we do not need to account for all of them because carbon is a solid. That does not matter for me. So carbon, solid, does not matter. I will not include it in my equilibrium constant. Next question, which substance goes on the denominator? The denominator is going to be the water, or A, that I have listed there, water, because it's products over the reactants. The only reactant that matters for us is the water. So next, we can write our Kc value. It is the concentration, so brackets over CO, or of CO, times the concentration of the hydrogen, divided by the concentration of the water. Now notice that none of them were raised to a coefficient because none of them have coefficients. All of the coefficients in my balanced reaction is 1. So I only have the concentration values. So again, it'd be the concentration of H2 times the concentration of CO, and that value would be divided by the concentration of H2O. So I'd have to be given some values. So let's take a look at this problem. Which of these would be the equilibrium expression for the reaction of N2 plus H2 in equilibrium with NH3? Well, first of all, I need to have a balanced reaction because that's not balanced there. So to get it balanced, I would put a 3 in front of the H2 and a 2 in front of the NH3. So products over reactants, all of them are gases, so I don't have to disclude any of them. All of them are included. So products over reactants, I have my NH3, which has a coefficient of 2, so it's NH3 concentration squared. Well, I can see right away that the only one that has NH3 on the top squared is D. But let's see if the rest of them work out. So I have N2, that has no coefficient, so just the concentration of N2 times the concentration of H2, and the coefficient we said would be 3 raised to the third power. So D is the correct answer for this practice problem. The next one, we have a combination or synthesis reaction of hydrogen and iodine gases producing hydrogen iodide gas. At a certain temperature, the equilibrium concentrations are H2 plus I2, and both are 0.15 moles over liters, and that of the HI is 0.50 moles over liters. At this temperature, the numerical value of the equilibrium constant is one of those. So we want to first write a balanced equation. H2 plus I2 goes to 2HI. That's our balanced equation for this one. H2 plus I2 goes to 2HI. Well, I have to look at my values. I have HI as my only product, so I would find the concentration of that, 0.50 moles over liters, and that value is going to be squared because the coefficient in front of HI is 2. So 0.50 squared divided by my concentration of my hydrogen times my concentration of my iodine. So it would be 0.15 times 0.15. When I calculate all of that out, I get a value of 11. So A is the correct answer.